Hi, and welcome back to MA 211. Let's talk some more about numerical methods. We talked last time about Euler's method, and suppose I have an ODE that I want to solve, like this one. We worked on this actually last class. And I'd like to approximate y at time 5. Now, we talked last time about varying step sizes. We could choose to take one single step from time 0 to time 5, which would be a fairly large time step. We could take 5 steps of length 1. We could do 10 steps of length a half, and so on and so forth. And now the question is, how much is it going to gain? Or how much am I going to gain by using smaller steps? We said before that using smaller steps gives you better results, and that's true. But how much better results? Is it worth the extra work? Obviously, it's a lot more work to do 10 steps to get to time 5 than it is to do 5 steps to do time 5, and that's more work than it is to do 1 step. Okay? So I actually did calculate the exact solution to this differential equation. I calculated it. And the reason I calculated it is that so we could investigate how well we're doing. So I calculated the solution to this ODE, and I evaluated it at time 5, and this is a full 16 digits of accuracy that we have right here. All those digits are correct. The real solution evaluated at time 5 is this number. Okay? And then ... And then what I did is I used Euler's method with differing step sizes. So first I did step size a half. So I had to take 25 steps using step size a half, and my approximation using step size a half to y at time 5 was 1.8260347. So it was this number. Alright, and then I calculated the error. I took the absolute value of the real value at time 5 right here minus the approximation using step size a half at time 5, which is right there. That's what this number is. And we can see there's an error of about 0.05 in my approximation. That's not terrible, but it's not great either. So what would happen if instead of using step size 1/2, I use step size 1/20th right here? Well, I got a new approximation to the value of y at time 5. It was 1.88. We can see that it's better than the previous solution, or the previous approximation, and that our error is about 0.0065 and change. So it's roughly 10 times better. I used a step size that was 1/10 the previous step size, and my error was about 10 times better. And the same pattern holds here. I used a step size of 0.005, and I got an error that was roughly 10 times better than the previous error, and so on and so forth. That is a pattern that holds in general. With Euler's method, reducing your step size by a factor of 10 decreases the error in your approximation by, roughly a factor of 10. Okay, and that's true for most differential equations that you're going to come across. Using Euler's method, reduce the step size by a factor of, say, alpha, you'll reduce the error by a factor of alpha. So that's quite nice. Okay, let's go ahead and take a look at a different numerical method. It turns out there are all kinds of numerical methods in the world. Okay, I'm going to take a look at something called the improved Euler's method. So just like before, I'm going to assume we know the value of y at some time, and I'd like to compute the value of y at some later time t plus h. So I want to take a step of length h and approximate y at that time. Let's see. Fundamental theorem of calculus says that y at time t plus h is just y at t plus the integral from time t, from the start time to the later time of y prime. Okay, that's what it says. So, what can we do? Obviously, this integral is the trouble part. We know this, but we don't even have an expression for y. We don't have an expression for y prime. We can't calculate that integral. So what we can do, Let's see, we could use the left-hand rule to approximate that integral, right? The left-hand rule says you evaluate the integrand at the left-hand side of the interval and you multiply by the width of the interval, and that's about the integral. So y at time t plus h is about y prime times h, and y prime at time t, we have an expression for that. This is just Euler's method. This is an alternate way of deriving Euler's method. You say, I just approximate that integral using the left-hand rule. There's an alternate way to do that, though, right? Remember, you could also say, remember the integral from a to b of some function, f of x dx, is about 1/2 the width of the interval times f at a plus f at b, right? That's the trapezoidal rule. You just, let me erase the 1/2 here. You multiply the width of the interval by the average of f at a and f at b. So we could go ahead and use that here, right? I could replace this integral with y prime evaluated at t, which I know, or which I can calculate, and then y prime evaluated at t plus h, which I don't know. Okay, so that's what I've done here. I've said y at time t plus h. You could estimate it as y at time t plus the average of y prime at time t and y prime at the right-hand side of the interval, which is y prime at time t plus h. And then you could calculate both of those by plugging y at time t into f, the right-hand side of the ODE, and f at time, or plugging y at time t plus h into the differential equation. So the problem with this is this guy right here. We said y at time t plus h, it depends on y at time t plus h, which we don't know that. That's what we're trying to approximate. So what we're going to do is we'll get an estimate at y at time t plus h using Euler's formula. So the first thing we'll do, we want to approximate y at time t plus h. We know y at time t. We'll get an estimate at of y at time t plus h using Euler's formula, and this is called a predictor corrector method. This step, I'm going to make a prediction about y at time t plus h, and now I'm going to plug this value of y at time t plus h into here, and I'll get a corrected value for y at time t plus h right here. Okay, so y at time t plus h is going to be y at time t plus h over 2. You plug y at time t into the ODE, you plug y at time t plus h, your approximation to that into the ODE, and you get a new approximation to y at time t plus h. So this is called the improved Euler's method. And it turns out it's more accurate than Euler's method, and we can see how much more accurate in a minute here. So let's take a look at the same ODE as before. Again, we'll use a step size of 1/2, just like we did in the last video, and I want to go out to time 2.5 again. So the first thing I do, I know y at time 0. That's 1. The next thing I do is I make an approximation to y at time 0.5 using Euler's method. So this should be y at time 0 plus 0.5 times y prime at time 0, which is sine of 0 times sine of 1, right? I had to plug in 0 and 1 into the right-hand side of my ODE up here. And if you do this, you get 1, okay, because sine of 0 is 0. And now I have, now I have an approximation to y at time 0.5. Now I make a new approximation to y at time 0.5. I say it's y at 0 plus my step length over 2, 0.5 over 2, times y prime at time 0 plus y prime at 0.5. So this is going to be f evaluated at 0 times y evaluated at 0, and y evaluated at 0 plus f evaluated at 0.5 and with y evaluated at 0.5. Okay, and my y star at time point 5 is sitting right here. And if you calculate that, you get 1.177. Okay, so now I have my value of y at time point 5. I can use that to do an Euler step from time point 5 out to time 1. So I can say this is y at 0 plus my step length of 0.5 times my f at 0.5 comma y at 0.5. So that's no problem. My y at 0.5 is sitting right here. I can plug that all. Oh yeah, my f is right here. It's sine of 2t, sine of y. It's just the right hand side of the ODE. And if you do that, you get 1.566. So that's my initial estimate of y at time point 1. I can correct that estimate using the improved Euler's method. This is y at 0 plus 0.5 over 2 times f at 0.5 comma y at 0.5 plus f at 1 comma my old estimate of y at 1. And if you do that, you'll get 1.599. Okay. I can now calculate y star at 1.5. Again, that's using an Euler step. That's y at 0 plus 0.5 times f at 1 comma y at 1. And that would give you 2.053. And now you go ahead and calculate y at time 1.5. So that would be, oh, these are all wrong. This should be y at time 0.5 here. Right, and now this is y at time 0.5. And this is y at 1. Okay, so now this would be y at 1 plus my step length over 2 times f evaluated at 1 and y of 1 plus f evaluated at 1.5 comma y star at 1.5. And that, if you do that, you get 2.053. No, you get 1.857. Okay, and you can just keep doing that for as long as you like. And I really, the thing that I want you to know, you need to know how to calculate these things from memory. Okay, so you need to know, I say, you do Euler's method, you do improved Euler's method. You know what those methods are, okay, and how to use them. Let's see. Now, error in improved Euler's method. So let's repeat the calculations of the previous section. I'll solve the same ODE. I'll go ahead and I'll try to approximate y at time 5 using improved Euler's method and different step sizes. So, if I use a step size of 0.5, I get an estimate of 1.78. Remember that my true solution is 1.88, so I'm only off by 0.09. I reduce my step size by a factor of 10, and my error goes from 0.09 to 0.0008. So about 100 times better here. Again, I reduce my step size by a factor of 10, and my error again goes down by a factor of about 100. And the same here, and same here. And this pattern again holds true in general. If you use an improved Euler's method and you reduce the step size by a factor of 10, then the error tends to go down by a factor of 100. And in general, if you reduce the step size by a factor of alpha, the error goes down by a factor of alpha squared. Okay, so that's very good. Obviously, improved Euler's method takes more work. Each step takes an Euler step and then a correction step, but it's more accurate. Okay, so these are two methods that are used for approximating solutions to ODEs. There's a whole wide world of numerical methods for ODEs, and if you're interested in this, I encourage you to take, say, MA 332 or MA 433. And that's it.